Hello. Okay, a few people are in. You should see the desktop and you should hear me. Is everything saying okay at this point?
Yeah.
Okay, great. Thank you. Okay, there's still a lot of people, only about half people are here. So have to wait a minute or two while people come in. Okay. Okay, people are joining the Zoom meeting. Okay. Okay, today we're gonna finish looking at some of these examples on race conditions, and then also start looking at some of these examples on Java threads. Okay, so first I'm going to download the race conditions example, and we're going to do one more example from that folder on race conditions. Just to, it's kind of a nice example. It's an example that's you see a lot in a lot of books and web pages. So it's I think it's a good example to do. Okay. Okay, so what I want to do, it's this example here starts out with number 6, 6, 7, 8, 9. Okay, so this set of examples here. Okay, now remember a race condition. If I go back, let's do the real simple one. A race condition is when two threads share a variable. Okay, like in this example, I've got with the variables up here. This was the shared variable. Both two threads were incrementing that variable. Okay, but each thread would, so what would happen was one thread would get a copy of the variable, increment it, increment it, so it'd keep the old value and the new value. So the old value is what it was, and the new value is one more. Then it would check here, and they wouldn't be one more. Remember that in between this thread getting this variable and getting it a second time, the other thread could have gone in there and grabbed the same variable. So two threads are sharing this variable, and the thread thinks of it. If you don't think concurrently like threads, you just read this as if it was CS1 a CS1 class. And if you read this like a CS1 class, you say there's a variable, get a value of it, take the variable, increment by 1, store its value again, and so then these two variables differ by 1. And it's it's hard to explain how that could not be different than 1. But the issue here now is that this is not the only code running. This code here is running simultaneously, and this code down here is accessing the same variable. So it could be incrementing that variable. So in between lines 62 and 63, line 80 might run. If line 80 runs in between 62 and 63, then there's 2 increments of count. So then this difference isn't 1. And in fact, a lot worse than that can happen. These things don't have to be running at the same time. They could be running alternatively on different CPUs. So this could run on one CPU. Then that CPU stops running this program. Then the CPU goes over here and starts running this program. The CPU could run this loop 1,000 times. So it would increment count 1,000 times. Then the CPU will stop running this, go back over here, and then the CPU will pick up at this line, and now count is 1,000 more than it was before. Because in between lines 62 and 63, the CPU went over to here and ran this loop 1,000 times. So shared variables are when a variable can be accessed by 2 different threads. Okay, and we solved that, we fixed that in this example by excluding, see, we're using this thing called mutex, something that mutually excludes threads. So we solve the problem here by saying, well, if one thread wants to do these 2 steps, then it should say, I'm the only thread that can do them. I'm going to mutually exclude any other thread from running while I'm in doing this. Okay, so while this thread is doing this stuff here, it owns that lock. So if some other thread tries to go over here and start, if some other thread tries to go over here and start this, it's going to get stuck on the lock. Now it's the same lock. It has to be the same lock. You can't use lock 1 here and lock 2 here. Then they're just, it's like 2 different bathrooms. This lock makes this essentially the same room as this. We called that room a critical section. A critical section is a chunk of code that only one CPU can be inside of at a time. So it's sort of like a private bathroom, a private room. You put a lock on it and only one person can enter, then they lock the door and then nobody else can enter it. Then when they're ready to leave, they unlock the door. Except that the funny thing here is that the door's got there's 2 places where you can enter this room from. Yeah, it's like a room that's private, but it's got more than one entrance to it. But if you lock one of the entrances, you're locking both of the entrances. The analogy is kind of hard. Yeah, the analogy, one of the things about multi-threaded code is people talk a lot about analogies, but the analogies are always kind of weird. So in a sense, it's like a private room with 2 entrances, but when you lock one entrance, you automatically lock the other one simultaneously. So if you enter this room and lock it here, you've also locked it from here too. This is the same room. These 2 lines of code and these 2 lines of code are a critical section. Only one CPU should be allowed in at a time. Okay. Now let's look at a little bit more subtle example of a race condition where 2 threads are sharing a variable. Okay. Okay. So this program is going to create 6 threads. So the main method comes in, okay? The main method, well, there's the thread function declaration. You have to declare the function before you can use it. So there's the thread function, there's its declaration, okay? Then I'm going to create 6 threads. So here's a constant with the number of threads. I need the ID numbers of all 6 threads. So I need a thread ID array. Okay, I need an array to hold an ID from each one of the 6 threads. Here's a loop that creates the 6 threads. So it's going to call create thread 6 times. Okay. Each thread stores its thread ID number in this array. This is, we haven't said what this thing is, so we don't worry about it. It's just null. All 6 threads run in the same thread function. So we remember we talked about that the other day. The function isn't the thread. The thread is a thread control block. So I'm now creating 6 thread control blocks that all point to the same piece of code. So I'll end up with 6 independent threads running in that same piece of code. And we drew a picture of that. You know, there's really nothing odd there. It's just there's a chunk of code in memory, and there can be as many as 6 CPUs stepping through that same chunk of code. So I'm creating 6 thread control blocks, all using that same thread function. Okay, then here I give each thread it's the integral. See, the 0 thread gets I equals 0. The first thread gets I equals 1. The next thread gets I equals 2. The next thread gets I equals 3. So this is the thread parameter. Okay, that's this guy here. Okay, so this is a pointer to void. Now pointer to voids are like object references in Java. They can point at anything, except you can't really use them because you don't know what they're pointing at. But I know that it's actually pointing at an integer. So I take that pointer to void, cast it to an integer pointer, then dereference it. And up here, I'm creating a pointer to an integer. See, it's an int. Okay, so I take the address of I and pass the address of I to this thread. Okay, the thread, since I wrote it, I know what I passed to it. I know that I passed it a pointer to an integer. Okay, right. So every time, one of the tricks about using threads is you can't use other people's threads because unless you know exactly what their thread functions point at, you have no idea how to use these parameters. The parameter is declared as pointer to void, which means it could be pointing at anything. You cannot dereference a pointer to void. C won't let you do that. So to dereference a pointer to void, in between that, you have to say, but I'm going to cast it as something else. So I'm going to cast the pointer to void as a pointer to int, then dereference the pointer to int. If it's not really an int, I'm just going to be reading garbage. If it was really a double, or if it was really a string, I'm just going to read nonsense here, because here I'm saying it's an int, but up here I don't. I have to know that it really is an int. But I do know that here. This is the address of an integer. Okay. All right. So I will be 0, then I will be 1, then I will be 2, 3, 4, 5. So each thread will get its variable. Okay. Now compile this. Okay, and run it, and it won't run the way we think it does. Okay. Now look at the output. See, each thread says hello from thread, then their parameter number. Okay. Notice that the parameter number 3 got used twice. The parameter number 6 got used 4 times, and we never saw 0, 1, 2, or 5, or 4. We never saw 0, 1, 2, 4, or 5. So we saw 3 2 times and 6 4 times. Run the program again. We got 6 5 times and 4 once. Notice every time we run the program, here we got 6 6 times. Every time we run the program, we get something different. That's a sign that we have a race condition. Something's not quite right here. The program's not doing what we thought. Yeah. So we have to analyze the program more carefully to see what's going on. Okay. Now, what's going on is that when I create this thread, I'm pointing to the variable I. So that means this I is actually shared by all the threads. The mistake here is that I'm not giving each thread a new variable. I'm making all these threads share that variable there. They're actually all sharing that one variable. So I'm giving each thread the address of the same variable. Now what's in that variable is changing. Okay, but here's what happens. I create the first thread, and it points at I. Maybe, and at that point I has 0 in it, but the thread maybe doesn't start yet. Then I gets incremented to 1, and I create another thread. And right now the address of I holds 1 in it. Now that's the same I as I gave the first thread. So now the first 2 threads both see I with 1 in them. Now maybe neither one of the threads even starts yet. They don't have to have started yet. The scheduler may not start them. Now I increments again, then I go in and I create a third thread and give it the address of the same variable I, but now I has 2 in it. Now I have 3 threads all seeing the same variable I, and it has 2 in it. Now maybe all 3 threads start this instant. Then I'll get 3 threads saying hello from thread 2. So I'll get, that's how I got here 3 3. What happened here was that this would have been the thread 0 and thread 1, but by the time thread 0 and thread 1 started, the I had been incremented up to 3. Okay, the I here had been incremented to 3. So these 2 threads started at the same time. This thread here and this thread here, they started at the same time, but when they started, the I had already incremented up to 3. Okay, then the I started more threads, and then the other threads didn't start up until the I had gotten up to 6, which is its last value. So that means that threads, so this would have been thread 0, thread 1, thread 2, 3, 4, and 5. Those threads got created. None of them started yet. Then at the very end, after all the threads have been created, then all of a sudden all the threads started up and they saw the same, they're all looking at the same I, and by then that I has 6 in it. Okay. And with the same thing happened, that's exactly what happened here. Here, the very first thread started up when I was 4, and all the other threads started up when I was 6. And now notice that the quirky thing is, this would have been the first thread. So when that thread got created, I was 4, but it didn't finish running until this other thread ran before it. So the stuff is very tricky to read. So this would have been the first thread. This would have been thread 0. When by the time it got created, I had incremented to 4, but it got started printing up. But at the same time, this thread managed to print its stuff out before. Well, see here, see this H here? This H came from him. See how he's missing his H? So that thread started with I equals 4, but then he got blocked. Then all the other threads started. By the time the other threads started, I had already been 6. Then the other threads do their output. Then we went back to this thread that had started way back here with this H, printed the rest of its output, and then did one more of the outputs. So that H came from the very first thread, and that thread, even though it was given when it was started, I was 0. By the time it actually runs, actually when it was created, I was 0. By the time it actually runs, I is 4. But then when it runs, it only manages to spit out an H before it gets blocked again. Then a whole bunch of other threads run, and they all see I equals 6. Then we're back to this thread with the I equals 4 in it, and it finishes its run, and then another thread prints its output out. Okay, so this example is kind of, it seems that a lot of people make this mistake. You see this in every kind of textbook because it seems to be really common for people to think that if they're creating a for loop like this, that each one of these threads gets its own I. Okay, and that's not how this thing works. Each thread is not getting its own I. The threads are actually sharing I. Okay, so that they're all sharing they're sharing the address of that one variable I. And if the threads don't start up, if you run through this loop and create all the threads, if you create the threads before the operating system starts any of the threads, by the time they're started, I will already been up to 6. I will have gotten all the way up to 6. Okay, and that's what almost happened here. Yeah, one thread got started before I got to 6. And if you run this a bunch of times, eventually you'll get one kind here, 6, 6, 6, 6, 6, 6. Yeah. So that means that none of the threads started until after all of them have been created. Okay. None of these threads started until after all of them had been created. Okay. Okay. So this is a real kind of funny, subtle race condition. Now, if you're lucky, it's not likely to happen. You could create the first thread and it starts right away and sees I equals 0. Then you create the second thread and it starts right away and sees I equal 1. Then you create the third thread and it starts right away and sees I equal 2. But that's very unlikely to happen. The scheduler is very unlikely to do what you would want it to do, where you would create a thread, it would see the proper I, then you create the next thread and it would see the proper I. That actually, I think, almost will never happen. Okay. Most of the threads end up seeing 5 or 6 because most of the time the threads don't get started until after they've been all created. The operating system will create all the threads, and then after they've been created, see, this main thread will run this loop, creating all the other threads. And so essentially what this is the main thread has priority, kind of, and it runs and creates all these threads. And after all these threads get created, then the operating system says, oh, I should go run one of these other threads. Now here, the very first thread saw 3, another thread saw 4, then a whole bunch of other threads saw 6. Okay. It's hard to get a thread even to see the value I equals 0. Because to see the value I equals 0, the thread would have to be created and then started immediately before this loop even did this increment here. You'd have to create this thread, pass it that address, start the thread, get the parameter I. All that would have to happen before this increment happened. Okay, that's really not very likely to happen. When you create a thread, the operating system rarely starts the thread right away. when you create a thread, the operating system almost always just says, I'll do this later. So the idea that you would go in here, create the thread and start it, and then loop, it's not very likely. You know, people tend to think that's what happens is, oh, I create the thread and it starts running. Then I loop up here in increment I. Then I create another thread and it's running. And I loop up here in increment I. But that's actually very rarely the case. Usually it's, I create this thread and the thread is just sitting there. Yeah, it's been created by the operating system, but the operating system hasn't gone and touched it yet. Then you create another thread and the operating system just lets it sit there. Then you create another thread and the operating system just lets it sit there. It hasn't started them yet. Meanwhile, the I is changing on them. Okay, and you can just run this. Notice that you tend to see a lot more 5s and 6s. And this usually about the smallest number you see is 2. Here, 4s and 6s. 5s, 4s and 6s, 4, 5, and 6. You might occasionally see a 2 or a 3. There's all 6s. Again, there, all those threads got created and none of them were started until the very end of the loop. The threads didn't get started until this loop was all done. Okay. And see, I can keep running this. And notice I get something different every time. I'm trying to see if I get even something around 1 or 2. There's a 3. Okay. So the loop looped 3 times, then finally created a thread. A thread actually got started. Yeah. After about halfway through the loop, one of the threads actually got started. The very first thread didn't get started till the loop was halfway through. Okay, so you can see the very first thread finally saw the number 3. Yeah, see, we're not getting much. We're not seeing the number anything less than 4 very often. Okay, so okay, that's an example of a subtle race condition, because unless you're thinking very thread-like, you'll look at this code and it would seem to make sense that you create a thread, it gets the value 0, then loop, create another thread, it gets the value 1, loop. Oh, if I put a little sleep in here, oops, that should give the operating system time to catch that. This sleep should give the operating system time to actually launch that thread. Oh, I forgot to. Now this is a Windows function. It's not a standard C function, so I need to include. Okay, Windows has a sleep function with a capital S. Linux has a sleep function with a lowercase s. And the C language doesn't have threads in it. So the C language, see, I have to include pthreads.h to get threads, and I have to include windows.h to get sleep. Okay, the C language itself doesn't know anything about threads. Okay, now if I run this, there, 0, 1, 2, 3, 4, 5, nice and orderly. That's because that little pause there gave the operating system, as soon as this thing pauses, the operating system says, whoa, what have I got to do now? Well, I just created a thread, I might as well launch it. So the thread got created, this thread sleeps, the operating system says, what do I do now? And the answer is, well, I just created this thread, might as well launch it. So it launches right away. In fact, I'm going to make, this is milliseconds. This is 1,000th of a second. This is probably enough time to give the other thread, time to launch. Okay, so I'm sleeping for only 1 millisecond. See? Okay. In fact, you can do something a little bit different here. What would it mean to sleep for zero amount of time? It's not clear what that should mean. And what it means is, I'll show you, it's usually thought as yield. What it's saying to the operating system is, I don't need to continue. If you want to do something else, here's a good time to go do something else. So sleep zero is a way for a thread to say, I could continue or I could wait at this point. I'm yielding to the operating system. If the operating system wants to do something else, go ahead. Now, since the operating system just created this thread, yielding here might let the operating system start this thread, but the operating system might just say, no, I'm just going to stick with you. So it's hard to say what this will do. With this, the yield might let the operating system might decide, okay, you yielded, so I'll go ahead and start the thread. I'll start the thread we just created. On the other hand, the operating system might say, no, I don't want to switch to another thread. I'd rather just continue with your thread. So this sleep zero may or may not do what we want it to do. Okay, let's see if see, it almost did. See, the operating system was a little bit touchy here. Okay, the very first sleep did not yield. So, we missed the I equals 0 and the I equals 1. But at some point, the sleep did yield and we got a thread 2. So the very first thread saw 2 by the time it started. Okay, let's try it again. This time the yield didn't do much at all. We're back to, by the time the first thread started, it saw 4. So the yields didn't do much at all this time. Here the yields did a little bit, not as much as before. This was the best version. The yield actually, on the third loop, the yield actually did something. Okay, you can run it a few times. You'll get different results. Oh, here the yield did nothing. See, the operating system just did the yield. What happened was the operating system said, I'm not gonna let you sleep. You're saying sleep zero, which means that if the operating system doesn't want it to sleep, the operating system can just ignore the request to sleep. And it ignored these current threads and it just didn't go back and start any of them. Okay. On the other hand, sleep 1, even though it's only 1 millisecond, the operating system has no choice. I'm telling the operating system, put me to sleep for 1 millisecond. Well, for 1 millisecond, the operating system doesn't know what to do, so it might as well go back to this thread it just created. So this one definitely will put the threads in order. Okay. Now notice I'm solving the race condition, but not solving the race condition. I'm not actually solving the race condition. I'm actually artificially slowing my program down. I'm saying create a thread, then basically sort of force the operating system to start that thread. Then increment I, create another thread, and more or less force the operating system to create that thread. Now, if you run this a bunch of times, you might actually get a situation where even though the operating system sleeps this thread, it may still not run this thread. It could just go run some other program on my computer. My computer's got let's see, where's that number? There's this, it's got 3,000 threads to choose from. Okay, the operating system literally has 3,000 threads to choose from, and that the number of threads is changing all the time. So when I run this program, the operating system, when this guy goes to sleep, there's actually no guarantee that the operating system will start the thread that it just created. It could even just go say, well, okay, there's 3,000 other threads to go do. I'll go do one of those other 3,000 threads. Okay. But it turns out that most of the time, most of these threads are, the vast majority of these threads are what we call sleeping. They're not really running. This computer is not very busy at all. you can see that the CPU utilization is pretty small. So there's plenty of CPUs available. Even though there's 3,000 threads, probably 3,085 of them are not doing anything right now. Well, actually, probably right now there might be a few dozen threads running. See, the machine's using 18% of its CPU utilization. Probably a few dozen, maybe even a few hundred of those threads are running, but nowhere near 3,000 of them. Okay, but when I run this, the operating system pretty much, when I hit this sleep, the operating system pretty much says, well, this process just created a thread. Since we're running this process, we might as well switch to a thread in this process, not switch to a thread in some other process. So the operating system's thinking usually is, it's better to switch to a thread in the same process than it is to switch to a thread in a different process. Since this thread went to sleep and a new thread was just created, the operating system probably says, well, this thread just went to sleep, this thread just got created, might as well launch it. It's in the same process. So you see this nice behavior. Okay. Now, but again, if you don't sleep or if you just yield, you get, see, you're not, here actually we did see thread 3. Okay, so the very first thread was created about halfway through the loop, but that's actually unusual. Most of the time we get, oh, there's another 3. More often than not, you'll get this. Oh, look, this thread here, see, he was the first one to start. So he saw thread 3, he saw I3, but he only managed to print HE, then everybody else jumped in, then there's the rest of his. On the other hand, the second thread, this would have been the second thread. It saw a 4, but it didn't print anything. So it saw the 4, didn't print anything, and then one of the other threads jumped in. Actually, this HE was this thread here. And this guy's HE is probably this one over here. Somewhere over here. So it's it's hard to piece up what's happening here. But one thread was created when I was 3, another thread was created when I was 4, and the other threads were all created when I was 6. I shouldn't say created, I should say started. One thread was started when I was 3, one thread was started when I was 4, and the other threads all started when I was 6. Okay. All right. Now let's look at some other ways to solve this race condition. The sleep method is actually not solving the race condition, it's just avoiding it. The race condition's still there, and the operating system might just ignore your sleeps anyway. The sleeps aren't guaranteed to solve the race condition. The sleeps are just more likely to solve it, but not guaranteed to solve it. Let's look at a way that we can guarantee solving the race condition. Okay, so this doesn't necessarily solve it. So number 7 solves it one way. What number 7 does is, when it gets into this loop, it creates a copy of I and puts it into heap. So what it's going to do is, I is 0. You get down here, and I'm going to put a copy of I in the heap. So I malloc an int in the heap. I stick I in that int in the heap. Then I pass my thread that int in the heap. What that does is every thread now gets its own variable. There's no more shared variable. And this is a real important technique. You allocate in the heap a piece of memory for each thread. Okay, so just before I launch a thread, I allocate in the heap a memory location. Then the thread is going to get the pointer to his copy of I. See, here's where I copy the value of I into that malloc memory location in the heap. Okay. So when I create the thread, yeah, I get back the thread ID number. All the threads are created down here, but this guy is given, he's passed the pointer to the memory location in the heap that I created. Then when this guy does, now this doesn't change here, it's still dereferencing an int, but now this pointer is pointing into the heap. But it doesn't matter when I create that thread, that thing in the heap is going to be there. Once I malloc this thing in the heap, it stays there. It just, it actually, after I print it, I should free it. I mean, right now, oh no, I'm sorry, right here. See, here's where I free it. Once I grab it, I go ahead and free it. See, once I grab it and I copy it into this local variable, I can free the memory out of the heap because I no longer need it anymore. So I'll grab the value out of the heap, store it in a local variable, free the value from the heap, and then print the local copy. If I wanted to, I could print the heaped copy here and then free it after I'm done with it. Okay, so I could write, I mean, let me, here's another way to write the same function. Instead of making a copy of it locally, I could just take this and put it in here. And take this and put it here. Okay, so this thing gets a pointer into the heap. It prints out that pointer in the heap, frees that heap memory, and then returns. So either one of these will work. Okay, for now, I'll use the first version. Okay, either one of these is going to work. This one just makes a local copy. This is the more efficient thing to do. Make a local copy, because if you're going to use that variable many times, it's better to have a local copy. Since I'm only using it one time down here, I could just grab it when I need it and then free it. Though this is the pattern you would use more often in a C program. The values in the heap, you grab it out of the heap, make a local copy of it, free the copy in the heap because you don't need it anymore because you've grabbed it, then make use of the local copy. That'd be the pattern you would do more often. Okay, now compile this program, run it. Okay, now the program, the output's jumbled up because it's still a threaded program, but notice I've got 0, 1, 2, 3, 4, 5. Okay, now the threads didn't get run in the order they were created. Notice that thread 2 ran before thread 1, ran before thread 0, and thread 4 and 5 ran before any of them. Okay, every time I run this program, I'll get different weird outputs. Oh, that's kind of an interesting output. Notice the threads didn't clobber each other. So I got nice hello from threads, but they didn't run in the right order. Here, the threads clobbered each other. So the threads were literally running simultaneously. So they were both, so more than one thread was printing to the console at a time. Here, the threads got more or less run one after the other, but not in the right order. So thread 0 ran, then thread 5 ran, then thread 1, 2, 3, and 4 ran. Okay, actually, the funny thing is that thread 5 ran in the wrong order. So the last thread ran second. So they almost got the right order, 0, 1, 2, 3, 4, but the last thread was last. So that's kind of, you have no control over this. The important thing is you have no control over what the operating system is going to do to run these threads. Okay, here they got jumbled up, they clobbered each other, but you still get all the numbers, 0, 1, 2, 3, 4, 5. Okay, so each thread got its own thread parameter safely. There is no shared variable anymore. by putting the value, so I'm allocating 6 values in the heap and giving each thread its own value in the heap. Now let's see, and I could switch that other version of the thread function. This version, again, this version uses the value in the heap, then frees it. Okay, and it should run exactly like the other one did. See? Okay. Notice I've got a couple runs in a row where they didn't step on each other. Here they stepped on each other a little bit. The order, I have no control over the order. Yeah, these stepped on each other just a little bit, and the order is kind of funny. Here, zero. Notice the first thread did run right away, but then the third thread ran after it, then the fourth thread, then thread 1, then thread 2, then the last thread 5. So again, the operating system just kind of has its own idea of what order to run these threads in. They're more or less run randomly. Yeah, they're more or less, there's no real sense that these threads have any order to them or priority to them. So they more or less get run just kind of in a random order. Okay. All right. So this, like I say, this grabs the parameter out of the heap and prints it, then frees it from the heap. This one grabbed the parameter out of the heap and stored it locally, freed the value in the heap, then printed the local variable, which is, like I said a minute ago, that's probably the better pattern, because it's better to use a local variable. You don't want to keep grabbing something out of the heap. Dereferencing a pointer is more CPU instructions than using a local variable. It takes more CPU instructions to dereference a heap value than it takes to use a local variable. So this would be more, if you were going to use this local variable many times, this would be more efficient. Since we're only using the local variable one time, this is actually more efficient. Since we're only using it one time, we might as well dereference it exactly when we need it and then free it. So because we're only using it one time, this is actually the more efficient one, but this would still be the better pattern to use. Okay, so we solve the race condition by not sharing variables. Notice before we solved the race condition by using a mutex. In the example we looked at before, we used something called a mutex to solve a race condition. It turns out in the real world of programming, a lot of times when people find out they have a race condition in their program, they don't need a mutex or anything fancy like that. They actually just need, they did something like this example here, 6. They accidentally shared a variable when they shouldn't have. It turns out to be a really common mistake in programming, to accidentally share a variable. And then the solution is just make a copy of the variable. Like here, make a copy in the heap and then give the thread the copy. So I don't need something as fancy as a mutex. I just don't make a shared variable. And that's why this example shows up in so many textbooks, because it wants to emphasize that when you have a race condition, that doesn't mean you have to run to a lock or a mutex or a semaphore or something complicated. Sometimes you just need to think about your code and realize, do you really need to be sharing that variable? Why are you sharing a variable? Did you really need to be sharing it? Here, the sharing was mostly by accident. Okay. Now here's another way to do the same, to solve the problem the same way. Get rid of the race condition by not sharing a variable. Here we're sharing it by accident. So here's another way to solve that same kind of problem. Okay. What I'm going to do here is create 2 arrays. Okay. Notice that I didn't have a problem with the thread IDs because every thread got its own thread ID array. Okay. So I'm going to use the same idea that I used here over here. So I'm going to create 2 arrays. So then each thread has its own slot in the thread ID array, and each thread has its own slot in the thread parameter array. Okay. And this is actually a pretty good way to solve the problem. Okay. Okay. So I'm not, now I don't have a race condition because each thread sees that slot in that array and sees that slot in that array. Okay. Now, this is still a pointer to an int. So this code down here does not change. Okay. Oh, notice that down here I had written it the more efficient way, or the other way. Notice here I had written it in the way, oh, here I can't free it. Okay. Notice that here, oh, in this example, this was the copy of the integer, but it's in the heap. So I should free it. Okay. Because otherwise stuff just stays in the heap forever. So if you don't free things, they'll just end up staying forever in the heap or until your program terminates. In this example, the variable is not in the heap, it's in this array. And this array is actually in main stack. It's not a heap variable, it's a variable in the stack of main. And you can't free stack variables. Okay, so this guy down here, basically what he does is he gets it out of that. Well, actually, here's what I could do here. I could make this thing one line less. So here's one way to do it. What he's doing now is he's taking the variable out of that array and making a local variable out of it and printing the local variable. I could also do it this other way, analogous to what we did before, could just take this thing and put it in here. And print directly from inside the array. I don't need to make it, I don't need to copy it into a local variable. Again, if you're going to use this parameter many times, you're better off copying it to a local variable than using the local variable. Since we're only using it one time, we can just access it directly in that array. Okay, so either one of these will work. Right now, I'll use the one that makes a local copy. So here's the one that uses the local copy, but neither one of these should free it, unlike this example, because again, here, this guy is in the heap, so I should free him once I'm no longer using him, so that I return the memory to the heap. This guy is in a stack variable, so you don't free things that are in a stack variable. That variable will be freed automatically when the program returns. Okay. Now, this program will run correctly. See, there's 1, 2, 3, 0, 4, 5. So I've got all the parameters correctly now. Okay. And I could also do it the way where instead of making a local copy of the parameter, now here I'm using I'm just going to print directly out of the array. I'm just going to access the variable directly in the array. Same thing, no different. They got jumbled up a little bit this time, but every time you run it, it'll be different. Thread 0 started up right away, but then was followed by thread 3, then 5, then 4, then 2, then 1. So the first thread got run first, the second thread got run last. Yeah, it's just keep emphasizing that you don't have much control over these threads. Once you create them, once you create a thread, it's really up to the operating system to decide what to do. Occasionally, when you create the thread, it launches immediately, but very rarely. More often than not, you create the thread and the operating system just creates the thread control block right away, but then doesn't use it for a while. So create thread will immediately create the thread control block. The thread control block, when this function returns, the thread control block has been created, but the thread doesn't have to have been started. So the thread control block will be there, but doesn't mean the thread is running. Usually it won't be running. when this function returns, more often than not, the thread you just created will not yet be running. The thread will just be created in the sense that the thread control block exists. Okay. All right. Now, here's another way to solve this problem. Now, this is a bad way to solve the problem. Okay. This is a quirky, and it's actually, depending on how you compile this, the compiler will give you a warning on this one. Like right now, I don't have the warnings all turned on. I'm missing one of the warnings here. So notice that even though I have minus warnings all, minus warning extra, pedantic, there's actually a warning in this code. And I'm not sure why this compiler is not giving me that warning. If I switch to Linux, here's the same code, but set up for Linux. If I open a command window here, switch to bash, and compile this using GCC, see, there's the warning in that number 9. This version of the compiler gives me the warning. The other version doesn't give me the warning. I don't know if it's because it's an older compiler that we're using. This Windows compiler we're using here is an older compiler, or I'm not really sure. See here, I'm only using minus W all. I'm not even using extra and pedantic. Standard C99. Here's the two compiler. Yeah. Here, standard C99, warnings all, warning extra, pedantic, but I don't get the warning. Over here, I'm only doing, where was it? I lost it now. Oh, I'm only doing warnings all, and yet I'm getting this warning here. But this is a much more recent version of GCC. Oh, I misspelled version. This is GCC 9. And over here, this is GCC 4. The GCC here, I remember it's version 4 of GCC. So it's several years old. So maybe they changed something, and maybe they changed the defaults for what minus W all means. Okay, but I'm getting a warning, and I'll show you in a minute what the problem is. Okay, so this example we're doing has a problem in it. It's not the right way to solve the race condition. Okay. Okay, let's analyze it real carefully. It's a little bit trickier program. Okay, so here's the for loop that creates the threads. The difference is this line of code right here. I take that variable I and I make it the parameter. I is the parameter. Now I have to cast it to a pointer to void. If I don't have that there, the compiler complains that this parameter is supposed to be a pointer to void. And it'll say, you gave me an integer where you're supposed to give me a pointer to void. Okay, you gave me an integer, but you're supposed to give me a pointer to void. So I solved that by just saying, okay, pretend this guy is a pointer to void. So I cast the integer to a pointer to void. Okay, and then it compiles. Now it's really an integer. Now these are all just numbers. Integers are numbers. Pointers are numbers. So what's the big deal here? See, the idea is that an integer is a number and a pointer is a number. So I can just say, take that integer and pretend it's a pointer. Then down here, I cast it not to a pointer to, here I just cast it back to an integer. See, then I know that this guy is really an integer. I cast it to a pointer to void, but then down here, I cast it back to an integer because that's what it really is. Okay. Now, this should be considered really flaky. I is an integer. I'm passing it to a pointer to void. This guy's a pointer to void, and I'm casting it to an integer. There ought to be something wrong here. Now, what the really thing that's wrong is, oh, I remember why I'm not getting a warning here. Oh, now I know what the difference is. This is an integer. Integers are 32 bits wide, 4 bytes. Pointers don't have to have the same size as integers. But this is a 32-bit compiler that I'm using here. This older compiler here is 32 bits. So that means that this pointer is also 32 bits. So this is a 32-bit integer being cast to a 32-bit pointer. Then this is a 32-bit pointer being cast back to a 32-bit integer. And as far as C is concerned, that's fine. Now, but what was going wrong over here? Now we can say more carefully what was going wrong over here. Open up the bash shell. Make the file, okay, and I get the warning. The problem here is this is a 64-bit compiler. See, if I go gcc -- version, oh, it doesn't even say it's 64-bit. It's been see, this one doesn't even say that it's 64-bit, but it actually is a 64-bit version of the compiler. Whereas the one we're using over here, see, if I go here and I open a command window here, here's the compiler. It's under E:/CS. I'm sorry, C:/CS 302/min, see MinGW32. Oh, I have to turn on verbose. I need verbose here. Okay. And MinGW32. See, everything is 32-bit here. See, it's a 32-bit. Now, if I go over here and I ask for verbose, see, I see 64. It's a 64-bit compiler. If I see 64 bits, and you'll see 64s everywhere here. It's a 64-bit compiler. Okay. And the other one, the older one, is in fact a 32-bit compiler. Now, the reason that's important is because ints are 32 bits on both of these compilers. An int is 32 bits. But in these two compilers, pointers are different. In the 32-bit compiler, a pointer is 32 bits. In the 64-bit compiler, the pointer is 64 bits. So now what goes wrong here is this guy is where things get complained about. Well, actually, in both of these, okay? Actually, I think it's this one here. This is a 64-bit pointer, and I'm casting it to 32 bits. So I'm throwing away half the pointer. That's what I get warned about. I'm chopping something in half. Chopping something in half is dangerous. Now, this is not usually going to be a warning up here, because this is a 32-bit thing, and you're expanding it to 64. Usually when you take something that's 32-bit and you expand it to 64-bit, you just add a bunch of zeros in front. That's not a problem. So you just take the 32 bits and add 32 zeros in front of it. Okay. But here you have to throw away bits. Okay. So this is line 43. Line 47 was the error. No, line 26. Oh no, it complained both places. Yeah, it did complain here. See, it complained at line 26 and line 43. So it didn't like either one. It complained about both of them. It complained about this one where I converted from 32 to 64, and it also complained about this other one where I switched from 64 to 32. So it complained about both of those casts. This is the trickiness of the C language. The C language is real subtle in these kinds of things. You have to actually start paying attention to, are my data types, how big are my data types? Which ones are 32 bits? Which ones are 64 bits? So here's a program that compiles fine in 32 bits, but doesn't compile correctly in 64 bits. Notice it doesn't fail, it gives you warnings. See, they're warnings. So it's not failing, though it may not run correctly. It may or may not run correctly in the Linux version, okay? Okay. All right, so I'm doing I'm solving the problem in a flaky way here, okay? So I'm solving the problem by saying, now, the key here is, why is this solve the problem? What happens here is, this takes the variable I and copies it from the stack of main into the stack of the thread, because it's passing a parameter to this function. So parameters are in the stack, but the main thread has a different stack than this thread. So what's real subtle here is that this line of code here copies a variable from the stack of main to the stack of the thread. Now, each thread has its own stack, so that means that each thread gets its own copy of this variable I. So there's no longer a shared variable. Some people use this trick. If you look at real C programming in threads, you'll see people use this trick, though you're warned not to use this trick, because you could have troubles if you switch from 32 bits to 64 bits, and different compilers can treat this thing in different ways. Now, again, see, it compiles fine and it runs correctly. See, it runs correctly, but it's not a good solution to the problem. Okay, so we get all the thread parameters are not, there's no race condition anymore. Okay, there's no race condition because instead of the parameter being shared, the parameter is being copied from one thread to another thread, from one thread stack, from the stack of the main thread to the stack of the new thread. Okay, and that gets copied before the thread gets created. So this gets copied into the thread stack when the thread is created. So if you talk about how you create a thread, you create a thread by creating a thread control block, but if you read the details, you'll see that you actually create two things to create a thread. You create a thread control block and you create a new stack for the thread. So most books will tell you that when you create a new thread, we only emphasize the thread control block when we're talking about it, but it's actually important to know that when you create a thread, you also create a new thread stack. Okay, so create thread creates the thread control block. It also creates the stack, and then this copies I from this guy's stack into the new stack. So then when each thread gets created, a new stack is created, and this thing gets copied from main's stack into the stack of the thread that's being created. Okay, and the biggest problem is that the I could be 32 or 64 bits, and the pointer could be 32 or 64 bits. The I is an integer, and this guy is being cast to a pointer to void, and you have to worry about whether integers and pointer to voids are the same size or not. Sometimes they're the same size, sometimes they're different sizes, depending on the compiler. The C language doesn't specify that. The C language doesn't specify what the size of an int is or what the size of a pointer is. In this version of GCC, int's 32-bit and pointer's 32-bit. In this other GCC, int was 32-bit and pointer was 64-bit. In some versions of GCC, ints are 64 bits and pointers are 64 bits, and then you won't get a warning from this. Then this won't cause a warning if the integer is 64 bits and the pointer is 64 bits. And some versions of GCC are work that way. They make an int a 64-bit. The pointer will be 64 bits, it's running on a 64-bit CPU. And some versions of GCC prefer to have 64-bit ints rather than 32-bit ints. The C language doesn't care. The C language just says there's a thing called an int, and every compiler gets to decide how big it is. And the C language just says there's a thing called a pointer, and every compiler gets to decide how big a pointer is. Every version of GCC or every version of a C compiler can have different combinations of the size of ints and the size of pointers. Same with doubles. The size of a double isn't really specified by the C language. There just is a thing called a double. Okay? And everybody pretty much has the same size doubles. It'd be real hard to find a language that didn't have 32-bit floats and 64-bit doubles, but that's not specified by the C language. So a compiler could potentially have 32-bit doubles and 16-bit floats, but most don't. But ints are all over the place. Ints are not very well standardized. So the 32-bit ints and 64-bit ints are both common, and pointers depend on the size of the CPU. If it's a 32-bit CPU, it's 32-bit pointer. If it's a 64-bit CPU, it's a 64-bit pointer. Okay, so those things vary. They vary a lot. Okay, all right. So this was a good example because the crux of the matter is that the shared variable didn't need to be shared, and this is important in a lot of code. When people end up with a race condition, they realize, oh, I'm sharing a variable, but I shouldn't have been. I don't need to be sharing the variable. I can just make a copy of this variable, and now I don't have a race condition because I made a copy of this variable. If you can avoid mutexes, you should avoid mutexes. Mutexes slow a program down a lot. These mutexes slow a program down. It takes a lot of work to lock a lock and unlock a lock. You can slow a program down by a factor of 10 easily by putting too many locks in it. Okay, it's well known that if you throw locks all over a program, you can stop race conditions, but you can end up slowing the program down to the point where it doesn't run very well. And there's other dangers with locks also. Locks can solve race conditions, but they can introduce their own problems. Okay, the main problem is that they can just slow you down too much. So a lot of times when people detect a race condition, instead of immediately jumping to a lock, they ask themselves, well, I have a race condition because I'm sharing a variable between two threads. Can I make a copy of that variable and not share it? Is it okay for me to have a copy of the variable? Sometimes you can, and sometimes you can't. Okay. In this example, this example here turned out that the copy was the right way to go. The sharing was the wrong thing. The bug was when I was sharing the variable. Sharing the variable was a bug. Making a copy was the right thing to do. Sometimes it doesn't matter. Sharing the variable may not be a bug, but it can cause a race condition, and copying the variable can eliminate the race condition. In this case, sharing the variable was a bug itself. And by not sharing the variable, we got the right behavior. Okay. Right. So the key here is to think about memory and how these threads are living all in the same memory. And we have to think hard about where these variables are. Like that's a variable in the stack. Okay. That variable in the stack, we were just giving an address of I to each thread. So all the threads were seeing the same I. It wasn't seeing 0, it was seeing I. See, people, if you think naively, you think, oh, I passed 0 to the first thread, 1 to the second thread, 2 to the third thread, but that's naive. I didn't pass 0 to the first thread. I passed the address of I to the first thread. When the thread runs, it just sees whatever's in I at that point. It was given the address of I. So when the thread runs, it sees whatever is currently in I. I didn't pass the value, I passed the address of the value. So by the time this program dereferences the address, the value in that address could have changed. So we have to start thinking of memory locations separate from memory values. I'm passing the location of the variable, not the value of the variable. On the other hand, this last version passed the actual value of the variable. that took the value and put it in the stack, not the address of the variable. It put the value of the variable in the stack. So this is the value of I. This one is the address of I. Big difference, the address versus the value. But this is flaky because I'm playing games with addresses versus values. So this is kind of a flaky thing to do. This is not flaky, but it's not what I really wanted. This is what I want, but it's flaky. I'm misusing the language. I'm casting an integer into a pointer. So it's what I want, but it's misusing the language. So then here's the really right way to do it. Here I create a memory location to hold the value. Okay. I create a memory location and copy that value into the memory location, then pass the address of that temporary memory location. And in this one, I created a different memory location for each value. I created an array of memory locations. So every memory location, see, every value is in its own memory location. Okay. So each value, notice that here I'm not even using the I's. Okay. Well, actually, yeah, I'm not even, see, these are the values I'm passing. Here I'm taking the address of the ith slot in that array, and the ith, like the third slot, is that one. Okay, so what this guy sees are these values. So I fill the array with unique values and then pass the address of each unique value in the array. And then this thing down here gets the value out of the array, but it's getting these values here. So for example, see, now if I run this program, the thread parameters are going to be, see, 10, 11, 12, 13, 14. Yeah, the thread parameter is what's in the array. It's not this I here. I is used to index into that array. So the thread parameters are what's inside here. Okay, so that's so here I'm creating memory. I'm creating unique memory addresses for each of the thread parameters, and I can just put anything I want in here. I could put random numbers in here. Oops. Okay. Now the threads get all the threads, just the threads are the thread parameters are those values there. Okay, but each thread parameter is in a different memory location. So the first thread gets that memory location, second thread gets that memory location, third thread gets that memory location. Each thread gets its own memory location. Okay, all right, so that's a long example, but it's it's an important example from the point of view of thinking about threads. A race condition that's really caused by accidental sharing, as opposed to a race condition where you really want the threads to share the variables, and where you really want the threads to share the variables, and so then they have to take turns sharing them. That's this example here. Then you need a lock. You want the threads to share the variables, but you need to make them take turns sharing the variables. Then you need a lock. But locks slow you down. Yeah. So when you see a race condition, you have to ask yourself, first of all, did I really need to be sharing those variables? If I did need to be sharing them, then you need a lock. If you didn't need to be sharing them, then you need to somehow separate them so that each thread gets its own copy of the variable. Okay. What about any question about the example? So it's a complicated example, even though it's ubiquitous. It's an example you see everywhere. Does anybody have any question about it? The main reason for doing this example is it makes you think. The example is it's another, helps you build a sense of how threads work. Okay, threads are notoriously tricky things to understand. Parallel programming and thread-based programming is notoriously considered one of the more difficult things that someone could do in the world of computer programming. Some people think it's the single most difficult thing to do in the world of computer programming. In general, it can be pretty tricky. Okay, so you need examples to build up a feel for how threads work. So usually you start with these simple examples like we're doing here and just keep hammering away at them and get a feel for how these simple examples do different things. Just get a sense that how these simple examples interact with variables and threads and the sharing and the locks. Okay, all right. So we're almost run out of time. Actually, oh, we did run out of time. Yeah, it's 4:46. I forgot to set a timer. I forgot to set the timer today, so we just ran out of time. Okay, so then on Thursday we'll start the Java thread examples, and we're going to start back from the beginning. We're going to look at what we're going to do with Java threads is write a bunch of examples that look almost exactly like the examples we wrote for the first thread examples, the C thread examples. So we're going to do some Java examples. These Java threads are as close as possible to these P threads examples. So you actually should read them in parallel. Download these P threads, download those Java threads, and they are written in parallel. Each Java thread example is parallel to one of the P thread examples. And then hopefully that gives us a sense of the difference between how Java and C do threads. There's certain things about them that are similar and certain things about them that are different. The Java threads are more confusing. The Java threads, I think, are, in a sense, way more confusing than the P threads. That's why we started with the P thread version. So I think we'll see that when we do the Java versions, they're a little bit weirder to read. Even though they're analogous to the P thread versions, they're a little bit weirder. Okay, any question? Any last question? Okay, so we'll start Thursday with the Java threads. So we'll start looking at how you create and launch Java threads, and then we'll see what I mean by how Java threads are weirder than P threads. Okay, so I'll stop sharing now and see you again on Thursday. Bye bye.